Here's a system design question that looks standard until you read the fine print. Design a web crawler, but make it decentralized. I've spent most of my career as a staff engineer building large-scale distributed systems, and this is exactly the kind of problem where the standard answer stops working. This video is for engineers preparing for system design interviews, mid-level to staff. You've heard of CAP theorem, partitioning, replication. You know what these concepts are, even if you haven't gone deep on all of them. And you've probably watched system design videos before. You can sketch the standard answer for most common questions. Here's the thing though, standard answers work for standard questions. But the moment an interviewer adds one constraint you didn't expect, the template stops working. Maybe it's a trust boundary you've never thought about. Maybe it's a consistency requirement that doesn't fit the usual model. Maybe it's a failure mode nobody warned you about. If all you have is the template, you're stuck. These videos aren't about templates. Each one takes a familiar system design problem, adds a constraint that breaks the standard answer, and works through it from scratch. The goal is to help you actually reason through the design, so when the question shifts, you can shift with it. So let's take a question and break it. Most people here design a web crawler and jump straight to the standard architecture. Workers, shared crawl queue, scheduler, dedupe store. That's perfectly reasonable for a centrally coordinated crawler, but it's not what this question is asking. The keyword here is decentralized, and that one word changes the entire problem. We're not building a crawler with a single control plane. We're building one where independent peers cooperate, peers that nobody centrally controls, peers that might not even trust each other. So what does decentralized actually mean? Because people mix this up with distributed all the time. Centralized means one control plane owns coordination, one scheduler, one queue, one authority calling the shots. Distributed means the system runs across many machines, but they might all report to the same control plane. A typical large-scale crawler is distributed. Thousands of machines, sure, but every one of them still talks to the same scheduler, pulls from the same queue, checks against the same dedupe store. One company still runs the show. Decentralized is different. The control plane itself isn't centralized. Peers might be operated by different people, join and leave on their own schedule, and may not trust each other at all. So the real question isn't how many machines you have, it's who controls coordination. Let that sit for a second, because the rest of this video comes back to that question over and over. Okay, let's look at the standard centralized crawler, not because we're going to use it, because we need to see which assumptions it depends on, and then watch them break. A centrally coordinated crawler has a few key pieces. There's a shared crawl queue, URLs waiting to be crawled. Then you've got workers that fetch pages and the parser that pulls new links out of whatever the workers bring back. There's a dedupe store that tracks what you've already crawled, a scheduler that controls ordering and timing, and an indexing pipeline that turns raw pages into searchable data. That's a lot of moving parts, but the way they connect is straightforward. It starts with the shared crawl queue. That's where candidate URLs sit. The scheduler looks at that queue and decides which URLs are ready to go, maybe based on how recently we hit that domain, maybe some other policy. Workers pick up those URLs and fetch the pages. The parser goes through what comes back and finds new links. Those links get checked against the dedupe store, and anything we haven't seen before goes right back into the queue. So it's a loop. URLs go in, pages come out, new URLs feed back in. And honestly, this works. It works because one organization controls coordination. That one organization decides who crawls what, keeps a single source of truth for what's already been seen, handles retries when something fails. When you're in control, none of this is hard. Now here's where it breaks. In a decentralized crawler, those assumptions are gone. There's no shared queue. There's no trusted scheduler. There's no single dedupe store. Peers show up, disappear, crash, become unreachable. Some might even be malicious. So the question comes back, who controls coordination? This time the answer is nobody, and that changes everything. The problem is no longer how do we scale our crawler workers, it's how do peers figure out who owns what when nobody's in charge? That's the question. Let's figure it out. To get a feel for how peers might cooperate, let's start with something most people have used: BitTorrent. BitTorrent takes a file, splits it into pieces, and lets peers swap those pieces directly. No central server holding the file. That gives us the shape for our crawler. Split the crawl work, let peers cooperate, remove the central coordinator. But it hides one hard question. Once the work is split, how does a peer find the right peer? In BitTorrent, before peers can exchange pieces, they need a way to find other peers who have the same file. One way to do that is a DHT, a distributed hash table. The lookup itself is spread across the peers. Our crawler needs the same kind of mechanism, but for a different question. BitTorrent asks, which peers have the file I need? Our crawler asks, who owns this crawl task? That's what we're building next. Before we build that lookup, let's pin down why ownership matters in the crawler. Peer A is crawling a page. The parser finds a new URL. In a centralized crawler, that URL would go back into the shared crawl queue, and the scheduler would decide what happens next. But in this system, there is no shared queue. So what should peer A do with that URL? The tempting answer is, peer A found it, so peer A should crawl it. But that rule breaks immediately. Discovery is accidental. The same URL might be found by peer A from one page, peer B from another page, and peer C from a third page. If every discoverer becomes the owner, then the same crawl task now has 3 owners. Now dedupe is split across 3 machines. Retry state is split. Crawl policy is split. Nobody has a single source of truth for that task. So the rule cannot be whoever discovers the URL owns it. The rule has to be deterministic. Given the same crawl task, every peer in the network should be able to compute the same owner. Peer A might discover the URL, but it may only be the messenger. The owner is whoever owns the key. That's the lookup we need. Given a crawl task key, which peer owns it? No central coordinator. How do we answer that? In a normal distributed system, you'd throw this into a table somewhere. Key range maps to owner machine. Done. But in a decentralized system, who owns that table? If one machine holds it, we're back to central coordination. So the table itself has to be spread across the peers. That's the core idea behind the distributed hash table, a DHT. It gives the peers a shared lookup rule. Given this key, who owns it? If you've seen consistent hashing before, this will feel familiar. If not, let's build it up. We start with a hash ring, a circular ID space. Say the range is 0 through 127, and it wraps around, so after 127 comes 0 again. Every peer hashes its own ID and gets a position on the ring. Keys, the things we want to look up, also hash into this same space. The ownership rule is one sentence. A key belongs to the first peer clockwise after that key's position. That's it. Say we have 5 peers at positions 12, 27, 52, 70 and 91. We want to look up key 63. Start at 63, go clockwise, the first peer we hit is 70. So peer 70 owns key 63. Take a second to sit with that, because the entire DHT is built on this one rule. Everything else is about how you route the query to the right peer efficiently. Now you're at peer 12 and you need to find the owner of key 63. How do you get there? The first approach is obvious. Every peer stores a full membership list, the position of every other peer on the ring. You look at your list, scan for the first peer after 63. The answer is 70, instant, big O of 1 lookup. But every peer is carrying big O of n state, a list of every other peer in the network. And when someone joins or leaves, that update has to reach all n peers. So membership changes cost big O of n messages per event. For a small network, fine. For thousands of peers churning, that's a lot of overhead. So let's try the other extreme. Each peer only stores one pointer, its successor. the next peer clockwise on the ring. Peer 12 knows about 27. Peer 27 knows about 52. That's all. Now to look up key 63, peer 12 asks, is 63 between me and my successor 27? No, so it forwards the query to 27. Peer 27 asks the same question about its successor 52. Still no. Peer 52 asks, is 63 between me and my successor 70? Yes, so 70 is the owner. 3 hops with 5 peers. But in a network with thousands of peers, this is big O of n hops. And each hop is a real network call, an RPC across the internet. So this is genuinely slow. So we've got two extremes. Full membership gives you fast lookup but expensive state. Successor only gives you cheap state but slow lookup. We want the middle ground. That's what a finger table gives you. Instead of storing every peer or just one peer, each peer stores a small routing table, roughly log n entries. The trick is how those entries are spaced. Each entry looks ahead at double the distance of the last one. The first entry looks 1 position ahead. The next looks 2 ahead. Then 4, 8, 16, 32, 64. And each entry stores the first peer at or after that position. What this gives you is the ability to halve the remaining distance to your target with each hop. First hop covers half the ring, next hop covers half of what's left, and so on. Let's see it work. Same ring, 0 through 127. 8 peers at 5, 20, 35, 50, 65, 80, 95, 110. We're at peer 5, looking up key 105. Who owns 105? First peer clockwise after 105 is 110. That's our target. Without the finger table, we'd follow successor pointers. 5 to 20 to 35 to 50 to 65 to 80 to 95 to 110. 7 hops. Now with the finger table. Peer 5's table has entries at +1, +2, +4, +8, +16, +32, and +64. The +64 entry lands at position 69, and the first peer at or after 69 is peer 80. The +32 entry lands at position 37, pointing to peer 50. We want key 105. Scan for the farthest entry that doesn't overshoot, that's +64, pointing to peer 80. Jump to 80. Now we're at peer 80. Peer 80 has its own finger table. Its +32 entry lands at position 112, pointing to peer 110. But 110 is past our key 105, so that overshoots. Its +8 entry lands at position 88, pointing to peer 95. 95 is before 105, so that's safe. Jump to 95. At peer 95, we check, is 105 between me and my successor 110? Yes. So peer 95 returns 110 as the owner. 3 hops instead of 7. Each hop, a different peer consulted its own finger table and halved the remaining distance. That's the core mechanism. It's not one peer doing all the work, it's a relay where every peer contributes a piece of the route. And this scales logarithmically. 1,000 peers, about 10 hops. 1,000,000 peers, about 20. Let me spell out both rules, because this is an easy place to get turned around. The ownership rule is, I own keys between my predecessor and me. More precisely, from predecessor to me, including me. The routing shortcut is, if the key is between me and my successor, then my successor owns it. More precisely, from me to successor, including successor. So at each routing hop, I don't have to ask every peer whether it owns the key. I ask whether my successor owns it. If yes, return the successor. If not, scan my finger table for the closest entry before the key and forward the query there. That's the whole algorithm. One thing to be precise about. When we say big O of log n here, we mean network hops, real RPCs across the internet, not local CPU comparisons. That distinction matters in interviews. Someone might ask, is that log n comparisons or log n round trips? It's round trips. In practice, you'd cache frequently used lookups and batch messages, but the baseline cost is big O of log n network hops per query. So let's put the three approaches side by side. Full membership gives you instant lookup, but big O of n state and big O of n update cost every time someone joins or leaves. Successor only gives you minimal state, but a single lookup can take big O of n network hops. Finger tables land in the middle, big O of log n state per peer, big O of log n hops per lookup. That's the trade-off that makes a large-scale DHT practical. Alright, back to the crawler. When a peer discovers a new crawl task, it derives a crawl task key from that task, a hash that lands somewhere on the ring. The peer calls DHT lookup with that key. The query routes through the ring using finger tables and comes back with an owner peer. The discoverer sends the crawl task to that owner, and the owner takes it from there. It manages the local frontier for its key range, handles deduplication, decides when to actually fetch. And that's the DHT's job in this design. It gives us one stable primitive. Given a crawl task key, find the owner peer. We know how to find the owner of a key. Now let's see what actually happens when a peer uses that lookup. Each peer runs its own local crawler: task queue, fetcher, parser, dedupe state, local index. Every peer has the same setup. Ownership decides which tasks enter that setup. Say a peer is crawling a page and the parser finds a new URL. It derives a key, calls the DHT lookup and gets back an owner. Two things can happen. If the owner is me, I check my dedupe state. Have I seen this task before? If not, I add it to my task queue. It'll get fetched, parsed and indexed like any other task. If the owner is someone else, I forward the crawl task to that owner peer over the network. The owner runs the same logic on its end, checks dedupe and queues if it's new, ignores it if it's already been seen. That's the core routing decision. DHT lookup decides where the task goes, the owner peer decides whether to actually process it. And then it repeats. When the owner fetches that page and the parser finds more links, each new link goes through the same process. Derive a key, look up the owner, send it where it belongs. Some of those links might belong to the same peer. Some might belong to someone else entirely. The loop keeps running. So what does this give us? Every crawl task now has a deterministic owner. Any peer can discover work and the work still routes to the peer that owns it. That's a working skeleton of a decentralized crawler. But this is the happy path. Healthy DHT, reachable owner, stable ring. A real design still has to handle new peers joining, owners crashing in the middle of work, and stale lookup results after the ring changes. On the crawler side, we still need to decide what the crawl task key actually is, how deduplication works, and how to avoid hammering a website. But all of those decisions get easier once the DHT layer itself is solid. So let's start there. How does a new peer actually join the ring? Let's say we have a ring with 3 peers, 10, 40 and 90. Each one knows its successor and predecessor. 10 points to 40, 40 points to 90, 90 wraps back to 10. Now peer 55 wants to join. It knows about at least one existing peer, say peer 10. How does it get into the ring? First, 55 needs to know where it belongs. It asks peer 10 to look up the successor of position 55. The query routes through the ring and comes back with 90. That makes sense. 90 is the first peer clockwise after 55. So 55 sets its successor to 90 and tells 90, I might be your new predecessor. 90 checks. Is 55 actually between my current predecessor 40 and me? It is. So 90 updates its predecessor to 55. At this point, 90 knows about 55 and 55 knows about 90. Peer 40 still has the old successor pointer to 90, and it will learn about 55 through its regular check-in. Every peer periodically checks in with its successor and asks, "Who's your predecessor?" When 40 checks in with 90, 90 says, "My predecessor is 55. 40 sees that 55 is between itself and 90, so it updates its successor to 55. Then it tells 55, "I might be your predecessor." 55 accepts. Now the ring is fully connected. 10 to 40, 40 to 55, 55 to 90, 90 back to 10. Local neighbor checks are enough for the ring to converge. That's the ring repaired. But 55 still can't route efficiently. It doesn't have a finger table yet. Remember, a finger table has entries that look ahead at doubling distances. Peer 55 is at position 55, so its first entry looks 1 ahead, position 56. The next looks 2 ahead, position 57. Then 4 ahead to 59, then 8 ahead to 63, and so on. For each entry, 55 runs a lookup through the ring to find which peer is responsible for that position. After these lookups, 55 has a working finger table and can route queries efficiently, just like every other peer. What about other peers? Their finger tables were built before 55 existed. Some of their entries should now point to 55, but they don't know that yet. Every peer periodically refreshes its finger table entries by rerunning those lookups. Over time, they'll discover 55 and update their tables. Until then, lookups still reach the right destination. They just take a few extra hops, because the routing isn't optimal yet. Correctness comes from the successor pointers, which are already repaired. Finger tables are just a performance optimization. Now ownership. Before 55 joined, peer 90 owned the entire key range from 40 to 90. With 55 in the ring, that range splits. 55 now owns keys from 40 to 55, and 90 keeps 55 to 90. But 90 is still holding crawl state, task queues, dedupe history for keys that now belong to 55. So 90 needs to transfer that state. What happens to new requests while the transfer is in progress? The answer is simple. 90 stays in charge until the handoff is done. Any new tasks that arrive for keys 40 to 55 still go to 90, because 90 is still the acting owner. 90 adds them to its state normally, and they get included in the transfer. Peer 55 doesn't start accepting tasks for its range until the transfer is complete and it has the full state. At that point, 55 tells 90, "I'm ready," and 90 stops accepting work for that range. Ownership has switched. After the switch, some peers might still have stale finger tables pointing to 90 for keys in 55's range. When 90 gets a task it no longer owns, it can simply forward it to 55. Over time, finger tables refresh and traffic routes to 55 directly. The system stays available during the entire join. No downtime, no global lock. Where does 55 get that first contact? Same as BitTorrent, a few well-known bootstrap nodes hard-coded in. They just provide an entry point into the network. So to recap the join, a peer finds where it belongs on the ring, links in by updating successor and predecessor pointers, builds its finger table through lookups, and receives its share of the state from the old owner. The ring keeps serving requests the whole time. No global coordination needed. But joining is the easy case. The peer is choosing to show up. What happens when a peer disappears without warning? Disappearing without warning, that's the hard case. We'll get there. But first, the easier version. A peer that leaves on purpose. A graceful shutdown gives us the mechanics, and the crash case builds on top. Let's start with a graceful leave. Same ring as before. 10 to 40, 40 to 55, 55 to 90, 90 back to 10. Peer 55 knows it's about to go offline. Maybe an operator pressed shutdown. Maybe there's a scheduled maintenance window. Before disconnecting, 55 hands everything off to 90. The task queue, the dedupe history, the whole key range from 40 to 55. 90 absorbs it all. Then 55 tells its neighbors. To 40, point to 90 after me. To 90, point back to 40. Both update their pointers. The ring closes the gap. 10 to 40, 40 to 90, 90 back to 10. Clean exit. That's the easy case. Now the hard one. Peer 55 crashes. No warning, no handoff. It just stops responding. Maybe the machine lost power. Maybe the process panicked. Maybe a backhoe cut a fiber line. The ring doesn't know 55 is gone, not immediately. Peer 40 still thinks its successor is 55. Peer 90 still thinks its predecessor is 55. But remember from earlier, every peer periodically checks in with its successor. When 40 reaches out to 55 and gets no response, it knows something's wrong. Here's the problem. If 40 only stored a single successor pointer, it's stuck. It doesn't know who comes after 55. The ring is broken at that spot. The fix is a successor list. Instead of storing just one successor, each peer keeps a short ordered list of the next few peers on the ring. Maybe 3, maybe 5. So 40's list might look like 55, then 90, then 10. Each entry stays fresh through the same periodic check-ins. When 40 detects 55 is dead, it falls back to the next peer in the list, 90. 90 responds. 40 sets its successor to 90 and tells 90, I might be your predecessor. 90 accepts. The ring is connected again. Finger tables across the network also still point to 55, but they fail over gracefully and refresh on their own. We'll come back to exactly how in a minute. So routing recovers, but what about 55 state? All the crawl work 55 owned, task queue, dedupe history, was sitting on 55's machine, and that machine is gone. This is where replication comes in. During normal operation, each peer continuously copies its own state to its next few successors. So before 55 crashed, it had been syncing its state to 90 in the background every few seconds. When 90 takes over 55's key range, it already has a recent replica. It promotes that replica to primary. It's not starting from scratch, it's picking up roughly where 55 left off. How close is roughly depends on how often state gets synced. If the sync interval is 5 seconds, the worst case is 5 seconds of work. Task 55 accepted in those last few seconds but hadn't replicated yet. Those could be lost. The more frequently peers sync, the smaller the window. So that's the leave. Both graceful and crash paths end the same way. Local coordination repairs the ring. No global announcement. Eventual convergence. Before we get to the bigger question, 2 follow-ups worth getting into. First, the stale finger tables I mentioned earlier. Successor pointers get repaired quickly through periodic check-ins. Finger tables refresh less often. So for a while after 55 crashes, peers across the network still have finger table entries pointing to 55. When a lookup goes through one of those stale entries, it times out. What happens then? Quick reminder of how finger table routing works. At each hop, the peer looks at its finger entries for the closest peer before the target key and forwards the query there. If the closest entry happens to be 55 and 55 is dead, the query times out. The peer doesn't give up, it just falls back to the next closest entry. Slightly longer path, same destination. And in the worst case, it falls back to its successor pointer, which is already repaired. So stale fingers don't break correctness, they just add extra hops. Over time, each peer refreshes its finger table entries. The dead references get replaced and lookup performance returns to normal. The pattern is consistent. Successor pointers carry correctness. Finger tables carry performance. When successors are repaired, the system is correct. When finger tables are stale, the system is slower but still right. That's stale fingers. The other thing is detection latency. There's a gap between when 55 actually dies and when 40 notices it. Periodic check-ins happen every few seconds, so in the worst case, you have a few seconds where lookups for 55's range get sent to a dead peer and time out before being retried elsewhere. The shorter the check-in interval, the faster the detection, but also the more background traffic. Most real DHT deployments tune this in the single-digit seconds. So the mechanics work, but here's a bigger question. What does this whole system actually guarantee? In the centralized crawler, the answer is easy. You've got a central database. You can do exactly once deduplication with a single atomic write. If the database says this URL has been seen, it's been seen, period. In a decentralized system, that guarantee gets expensive. There's no central database. State lives on owner peers and their successors, and any owner can crash. We already saw the basic mechanism in the last section. Each owner continuously replicates its state to its next successors, so when an owner crashes, a successor promotes its replica and keeps the work going. The question now is, how strong is that guarantee actually? What can still be lost? Two dials decide. The first is the replication factor. Call it K. K is just how many successors hold the copy. For data to be truly lost, the owner plus all K replicas would have to fail before replication catches up. With K equals 2 or 3, that's unlikely in practice. The second dial is the timing of replication. We touched on this last section. There's a small window between the moment the owner accepts a task and the moment that task gets replicated. If the owner crashes inside that window, the task lives on exactly one machine and it's gone. For most pages, that's fine. The web is full of redundant links and the crawler will rediscover the URL from somewhere else. But the long tail is different. Some pages have only one inbound link. If the owner accepted that URL and crashed before replicating, no other page will lead the crawler back to it. That URL is silently lost. This is the real cost of the window, silent coverage gaps on the long tail. So the design question is, how hard do we want to close that window? 3 mechanisms to choose from. Let's start with the 2 extremes, then the clever middle. Option 1 is pure asynchronous replication. The owner accepts a task, saves it locally, and copies it to its replicas a little while later. How long is a little while? That delay is the loss window, the gap during which the task only lives on one machine. So the choice inside option 1 is just how long that delay is. If you ship updates in batches every few seconds, the window is a few seconds. And if the owner crashes between batches, every task it accepted in that gap is gone because the replicas never got them. If instead you fire a network call for every single write, the window shrinks to one round trip, milliseconds. But every accept now costs you extra network traffic. The trade-off is straightforward. More network calls, smaller window. Either way, the long tail takes the hit on whatever falls in the gap. Option 2 is the opposite extreme, full sync. Every single write, initial acceptance, and every progress update waits for replicas to confirm before the owner accepts it. No window, ever. Every accepted task is guaranteed to land in the index, full at least once coverage. But you pay the latency cost on every write, and if a replica is slow or unreachable, the owner can't accept new work at all. You've traded coverage for availability. Option 3 picks the best of both, mix sync and async. The key insight, not every write matters equally. The most critical one is the moment the owner accepts a new task. So use synchronous replication just for that one write. It blocks until the replicas confirm, so the task can never be silently lost. Before the owner even acknowledges it, at least K replicas have it on disk. After that initial write, switch back to async for all the progress updates, which are higher volume but less critical. You pay a sync cost where it matters most and an async cost everywhere else. The trade-off across these is coverage versus latency. How strict and at least once guarantee do we want for the long tail, and how much latency are we willing to pay on every write to get it? Option 1 is cheap on latency but accepts a small coverage gap. Option 2 closes the gap entirely but costs you on every write and exposes you to availability problems when replicas misbehave. Option 3 closes the most important hole, task acceptance, at a small added cost over option 1. For a web crawler, that trade-off usually lands on the cheap end. Crawling is high volume and latency sensitive, The work lost in the window is mostly recoverable through redundant links. Slowing down every single write to save a small amount of long tail loss is almost never worth it. Most decentralized crawler designs pick option 1 and reach for option 3 if long tail coverage is a hard requirement. Option 2 almost never shows up in real designs, so the practical target becomes eventual coverage. Most reachable pages get crawled. Some pages get crawled twice after a failure. A small number of single link pages can be lost if the timing is bad. The price is duplicate work after failures and occasional long tail gaps from async replication. That sets the baseline guarantee. Now let's walk through the specific failure modes one by one. First, what if the old owner comes back? Maybe peer 55 was temporarily unreachable, a network blip, a long garbage collection pause. While 55 is gone, 90 takes over its key range. Then 55 comes back online. Here's the thing, 55 has no idea that 90 took over. It was offline when that happened, so it missed it entirely. From 55's own point of view, nothing changed. It's still the owner of keys 40 to 55, just like before. Now two peers are both accepting crawl tasks for the same key range. 55 is writing to its scene state. 90 is writing to its scene state. Neither knows about the other's writes. That's a split brain. The scene states diverge, so dedupe breaks. The same task can get accepted, queued, and crawled twice, once on each side, and there's no clean way to merge the two scene states afterward without picking a winner. Accept is ownership epochs. Every time ownership of a key range changes hands, the epoch increments. It's just a counter attached to the key range. When 90 takes over from 55, the epoch goes from, say, 3 to 4. 90 tells its replicas, from now on, only accept writes that carry epoch 4 or higher. Anything with epoch 3 or lower is invalid, reject it. That's a fencing token, which is a fancy name for exactly this idea. A number that says anything older than me is stale, ignore it. Now when 55 comes back, it still thinks it's the owner with epoch 3. It tries to write some new task to its replicas. The replicas check the epoch 3, which is below the current 4, and reject the write. 55 sees the rejection, and that's how it learns it's stale. At that point, 55 has to stop accepting new work, rejoin the ring, and discover who the current owner is. The core principle is simple. The ring decides ownership, not the peer. A peer's belief that it's the owner is only valid if its epoch is current. So far, we've talked about one peer failing at a time. The next failure mode is at the network level. What if the network itself splits? Say we have 6 peers on the ring, 10, 25, 40, 55, 70, 90. A network partition cuts them into 2 groups. 10, 25, and 40 can talk to each other, but not to 55, 70, or 90, and vice versa. Each side sees the other 3 peers as crashed. Both sides repair their successor pointers and form independent mini-rings. Both sides keep crawling. Both sides update their own scene state. Now you've got 2 separate crawlers running on overlapping key ranges with no coordination between them. When the partition heals, the ring reconverges through the same periodic checks. The scene state is messier. 2 sides made independent decisions, so some URLs got crawled twice and some were missed. There's no special reconciliation here. Normal crawling fills the gaps and dedupe catches the duplicates over time. A crawler gets away with this because fetches are naturally idempotent and the web has redundant links. Systems that need stronger consistency would have to reconcile explicitly. That's a different design trade-off. This is the CAP trade-off in practice. CAP stands for consistency, availability, and partition tolerance. The well-known result that when the network splits, you have to pick between staying consistent and staying available. You can't have both. In our case, during the partition, each side stayed available. It kept accepting and executing crawl tasks. The cost was consistency. The two-side scene state diverged and reconciliation becomes part of recovery once the network heals. So those are the failure modes: stale owner returning, network partition. They share one property. The blast radius depends on what state each peer owns, and that depends on the crawl task key. We've kept the key abstract on purpose. Time to open that box. What actually is the crawl task key? Remember, it's the value we hash to decide which peer owns a task, so this isn't a small detail. The same choice shapes dedupe, politeness, and default blast radius all at once. The key choice is a spectrum of granularity: full URL on one end, hostname on the other, and things in between, like hostname plus first pass segment. Each level trades load balance for coordination. Full URL gives the best load distribution. URLs scatter randomly across the ring. Big websites naturally spread across many peers. Dedupe still works. Each URL hashes to exactly one owner, so the dedupe decision is still local. The cost is politeness. With URL sharding, one site's pages spread across many peers, and each peer only rate limits itself. Nobody watches the total. The load a site actually feels is everyone's requests added up, and no peer sees that sum. And this isn't just a rare coincidence. When the crawler discovers a site, it pulls in a lot of that site's links at once. Those links go to different peers, and they all get fetched around the same time. So a small server can take a sudden burst, with no one to slow it down, and hammering a server gets you blocked. Same problem for robots.txt. Its crawl delay is set per site, but no single peer is in charge of honoring it. Hostname hash is the other end. All URLs from youtube.com go to one peer. That peer is the single authority for robots.txt, crawl rate, and dedupe for that host. Politeness is clean. One owner, one set of rules. The cost is hot shards. youtube.com has tens of millions of pages. One peer may not have enough fetch capacity for a host that large. UbiCrawler, one of the early academic decentralized crawlers, used hostname ownership and ran into exactly this problem. A middle ground is to hash hostname plus the first pass segment. youtube.com/watch and youtube.com/channel would map to different owners. This splits hot hosts while keeping some per path locality, but it also splits robots.txt and rate limit responsibility across multiple peers, so you're back to some coordination overhead. So how do we handle a hot host without giving up the single owner? Here's the key move. Keep one owner, but don't make it do all the fetching itself. The owner already keeps a few successor replicas from fault tolerance. Let those replicas act as helpers. The owner stays the brain. It decides what to crawl and enforces robots.txt, the rate limit, and dedupe. But it hands the actual fetching out to its replicas in small batches. They fetch the pages, parse them, and send the results back. So politeness and dedupe for that host stay coordinated under one owner, while the fetch work spreads across 2 or 3 machines. A truly enormous host might need a larger pool of helpers, but for almost every host, the replicas you already have are enough. There's also a completely different axis, where you assign ownership. Apoidea, another academic decentralized crawler, assigns URLs based on geographic proximity. A peer in Tokyo preferentially owns Japanese websites. The fetch latency is lower because the peer is closer to the server. But popular web regions, the US, Europe, become geographic hotspots and load balance gets worse. It's the opposite trade-off from pure hashing, which is topology blind but evenly distributed. So which one do you actually pick? It genuinely depends on the constraints. The interview move is to reason through them out loud, not to recite one answer. Start from hostname. For the common case, peers run by one organization where politeness is a hard requirement, it's the cleanest fit. One owner per host, a single authority for robots.txt, crawl rate, and dedupe. And hot charts don't force you off it because the helper mechanism absorbs the load. But if load balance matters more than coordination, you want big sites spread evenly across every peer. Full URL sharding distributes best. and you take on per host coordination to get it. And if peers are spread across the globe and fetch latency is what you're optimizing, proximity-based assignment crawls each region locally at the cost of lumpier load. So walk through the trade-offs and pick for the situation in front of you. With either choice, dedupe works the same way. Each URL hashes to exactly one owner. The owner checks its scene state. Has this URL been scheduled before? If yes, drop it. If not, enqueue it. One owner, one scene set, one decision point. That handles the design choices for what each peer owns. But there's another set of questions waiting. How much state can one peer hold? And how many peers can the whole network hold? Both of those come down to numbers, so let's actually run the math. It's the cleanest way to see which trade-off wins in which scenario. Storage first. Each peer owns many hosts and accumulates URLs over time. The question is how many total URLs one machine needs to track, and at what point an exact set stops fitting in memory. An exact hash set stores an 8-byte hash per URL. So the math is just 8 bytes times the count. 100 million URLs is 800 megabytes, a billion is 8 gigabytes. These are big numbers, but they fit in memory on a modern machine. At this scale, an exact set works fine. You get 0 false positives and simple implementation. Now compare that with a Bloom filter. If you haven't met one, here's the idea. It's a compact, probabilistic set that answers, have I seen this URL? Using a fraction of the memory. The catch is, it isn't exact. It can occasionally claim a brand new URL is already seen. We won't open up how it works inside. What matters is the deal it offers. Far less memory in exchange for that small error rate. How many bits per element? There's a simple rule. Roughly 1.44 times log base 2 of 1 over the false positive rate, where 1.44 is a fixed constant. Plug in 1% and you get about 10 bits per element. 10 bits times 100 million is a billion bits, which is about 120 megabytes. 10 times that, a billion URLs, is 1.2 gigabytes, far less than the exact set. The price is accuracy. At 1%, 1 in 100 new URLs gets incorrectly dropped, and 1% of a billion is up to 10 million pages the crawler never visits. Tighten the rate to 0.1% and the same rule gives about 14 bits per element, but the false positive rate never fully goes away. And a standard Bloom filter can't remove an entry. Once a URL is marked seen, there's no way to unmark it. So if a false positive flags a page the crawler never actually visited, that page stays blocked forever. At 10 billion URLs, the gap really opens up. The exact set stores 8 bytes per URL, so 10 billion URLs is 80 gigabytes, expensive even for a dedicated machine. The Bloom filter, at 14 bits per URL for that 0.1% rate, is 140 billion bits, which is about 18 gigabytes. That's over 60 gigabytes saved, and now the trade-off clearly pays off. So the storage answer depends on scale. At hundreds of millions of URLs per machine, an exact set is affordable and preserves accuracy. At tens of billions per machine, memory pressure pushes you toward a Bloom filter, and you accept a small coverage loss as the cost. The right call for an interview is to reason through the numbers. That's storage scale. Now the other dimension, network scale. How big can the peer network get? The DHT gives us big O of log n hops per lookup and big O of log n finger table entries per peer. Take 10,000 peers as our running example. Log base 2 of 10,000 is about 13, so lookup takes about 13 hops, each one a real network RPC. At 50 milliseconds a hop, that's roughly 2/3 of a second. The more interesting question is churn. Peers join and leave. Every time that happens, successor pointers update, state transfers, finger tables go stale. The system handles this, we've spent 2 whole sections on it, but there's a rate limit. Remember the 3 approaches from earlier? Successor only, full membership and finger tables. We compared them on state and lookup cost. Now add the third dimension, maintenance. Every entry a peer stores has to be refreshed periodically, say every 30 seconds. Still at 10,000 peers, watch how far apart the three land. Successor only keeps one entry per peer. Refresh that one entry every 30 seconds, and across 10,000 peers, that's 10,000 refreshes every 30 seconds. 10,000 divided by 30, about 333 a second for the whole network. Almost free. But the lookups are brutal. With a single pointer, you walk the ring one hop at a time, on average half of it, about 5,000 hops. At 50 milliseconds each, that's roughly 250 seconds, over 4 minutes for a single lookup, against well under a second for finger tables. Hopeless at this size. Full membership keeps all 10,000 entries on every peer, 10,000 times the refresh work, so about 3.3 million RPCs per second network-wide, just to stay current. Lookups are instant, but the upkeep crushes you. Finger tables land in the middle, about 13 entries per peer, so 13 times that 333, around 4,300 RPCs per second network-wide. That's 2 orders of magnitude under full membership, and lookups are still only 13 hops. The pattern is clean. Whatever you store, you have to maintain, so storage cost is maintenance cost. And this isn't just our 10,000 peer snapshot. Across n peers, it scales as big O of n, big O of n squared, and big O of n log n network-wide. Full membership goes quadratic at any size. Finger tables stay near linear. Same trade-off, same winner. Now, churn. If peers are churning faster than finger tables can refresh, say 100 joins and leaves per minute across the network, the finger tables never fully converge. Lookups still work because successor pointers are always repaired first, but they fall back to more hops, closer to big O of n in the worst case. The system stays correct, it just gets slower. In practice, most deployments stabilize at a churn rate where finger tables can keep up. If churn is too high, you can increase the refresh rate at the cost of more background traffic. The key insight is that successor pointers carry correctness, while finger tables improve performance. One thing worth naming before we wrap up. Everything in this design assumes that peers play fair. A peer can crash, fall behind, or come back stale, but while it's alive, it follows the rules and reports honestly. The harder world is a peer that actively lies. It says it crawled a page it never fetched, hands back fake links, or quietly corrupts its scene set so real pages get skipped. That's called a Byzantine fault, not a machine that breaks, but a machine that cheats. Bitcoin is a classic example of a system built for exactly that world. You can't trust any single node, so the network forces everyone to prove they did the work. Our crawler doesn't need that. In a system design interview, you almost never have to worry about nodes that cheat, so we assumed honest peers throughout. If there's interest, Byzantine fault tolerance is worth its own session, but it's a separate problem. Okay, that covers the base design. If there's one takeaway, I'd rather it not be, here's how to answer the decentralized crawler question. The specific question matters less than the reflexes behind it. These same constraints show up in almost any distributed system, and once you can name them, you'll know which tool to reach for. When there's no central coordinator to hand out work, you need a way for every node to agree on who owns what without talking to each other first. You hash the key onto a ring, and whoever sits at that position owns it. Every node runs the same hash, so they all compute the same answer independently. That's consistent hashing. When a machine dies, the state it was holding can't die with it, so you keep copies on the next few neighbors before anything fails. When the owner goes down, a neighbor already has the data and steps in. That's replication. When a crashed owner comes back, it still thinks it's in charge. Now two nodes both accept writes for the same key range, and their state quietly diverges. You stamp every ownership change with a counter. Writes carry that counter, and replicas reject anything with an old stamp. The stale owner gets refused, and that refusal is how it discovers it's no longer the owner. That counter is a fencing token. And when guaranteeing every piece of work runs exactly once gets too expensive, because it takes coordination on every write, the thing you're trying to avoid, you relax it. Run the work at least once and design it so a repeat does no harm. That's at least once with idempotency. Strong exactly once is genuinely hard in a distributed system. This is the practical alternative that most real systems reach for. One more thing. A lot of these design decisions, like which key to partition by, don't have a single right answer. Hostname gives you clean coordination. Full URL gives you better load balance. Geography gives you lower fetch latency. It depends on what the business actually needs. In an interview, the move is to reason through the trade-offs out loud. The interviewer wants to see you think, not recite an answer. If there's a system design topic you'd like to see next, drop it in the comments. That's genuinely how I pick what to work on. And if this was useful, a subscribe helps more than you'd think. See you in the next one.